conical pendulum problem, one of the things I want to emphasize is that in terms of what you're responsible for, there's kind of a final formula at the end of all this. You can't walk in and memorize the formula. You actually have to go through all the steps I'm going to go through to get full credit. I will be looking for these steps, especially at the honors level. And the question is about a conical pendulum. And a conical pendulum, I'll do like a quick sketch of this, a very rough indication of what does this look like visually in real space. So this is, you imagine the rubber stopper at the end of a string right here. And it's sweeping out this circular arc. And the circular arc goes like this. So the circular arc is like the base of a cone. And the reason it's called a conical pendulum is you can imagine if I look at it various times during this whole process, it kind of makes this circular cone shape. So that's why it's called a conical pendulum. What I'm interested in, and you can refer to the simulation to see exactly why this is the case in real time, the Walter Fent simulation. But I really want to do a free body force diagram. This is a circular motion problem, so I'm going to do a free body force diagram. Here's the pendulum. Here's the tension that's holding the pendulum. And here's the weight, force weight. There are components to this tension, and the components are going to be really important. These are the components to the tension, and what's really important to realize is that this component equals the weight. That's what balances it. It's also important to realize that this FTX is the component of the tension that provides the centripetal force. So the theme with all those centripetal force problems is what provides the centripetal force in this particular situation. And I've made it a little easier than the other one you encountered by telling you that is the angle with the vertical. I'm telling you it's the angle with the vertical. So the first thing you should always do in these problems is you write down F sub c equals mv squared over r. And F sub c in this case is ftx. I'm going to skip a step, and I'm going to assume some knowledge. I'm assuming that you can look at that, and you can look at this angle theta right here, and you can see that this piece is this piece, and you can imagine this right triangle in here. You can imagine this right triangle in here. And I'm going to write that as ft sine theta. Now, some of you are thinking, wait, I thought horizontal was always cosine. It's not always cosine. In this case, it's sine because that side that we're interested in, this side here that we're interested in, is actually opposite the angle. And if I pick it up and move it to make a right triangle out of it, you can see it there as well. It's actually opposite the angle theta. So ft sine theta equals mv squared over r. But I don't have enough information to proceed from there, so I need to write down another equation that has ft in it. And what you can see is that the ft cosine theta, which is this piece here, that's ft cosine theta, is equal to mg because it's equal to the weight. So I can solve for ft in preparation to substitute mg over cosine theta. I'm just getting ready to sub. Now look, I can take that ft and I can plug it in here. So I'm about to plug this expression in. So I end up with mg over cosine theta equals mv squared over r. Very important to see here that the masses cancel. if you divide both sides by the mass. Whoops, I made a mistake here. Anybody else see my mistake? I left out the sine theta. So I'm going to throw the sine theta on the outside. Sorry about that. But this is just sine theta times all of that. Sine theta, if I do sine theta times, if I do this times this, that's the same as doing the mg cosine theta times the sine theta. The order doesn't matter. So I'm just putting that in. Okay, so I'm just going to check off everything we know, and you guys can do the plugging and chugging. You can try it at your leisure. If I'm doing my plugging and chugging, I know theta is 20 degrees, so I can do sine and cosine of theta. G is 9.8. I was told that the distance from the center was 50 centimeters, but be careful. Make sure you use your R of 0.5 meters. Convert that to meters. And now I just have to solve for v squared. And when you solve for v squared, by taking the square root at the very, very end, you should get 1.34 meters per second. Now, if you want more practice, I'm not going to give you necessarily enough time to write down now. You can log on, and I've got 2 more problems written where you can go through the same process, and there are the answers. You're going to follow the same process. For this number 3, you're going to be solving for a slightly different variable, but with the same expression.